Hello friends, today I am going to talk about basic postulates and formulation of quantum mechanics. Now basic postulates. First is existence of state function. For a particle in one dimension, ignoring spin variable, there exists a state function psi x t, that means it depends on x and t both, which is called wave function, and it gives all information about the particle. Psi x t is in general complex. This concept can be extended to a system of particles with spin variables. Spin is some kind of angular momentum which cannot be explained in the framework of classical physics. Now, second postulate is that classical dynamical variables go over to operators, and the operators are something which act upon the wave function and they produce a new wave function. For example, position variable x goes over to x hat is x operator, and p goes to p hat is another operator, and x and p hat are operators corresponding to position and momentum variables respectively, and from psi x t we get x psi and p psi, and both are different states. Now, as far as the evolution of wave function with time is concerned, we note that total energy is E given by sum of kinetic and potential energy. So, E is equal to p square by 2 m plus v x t, and we now define a Hamiltonian operator which is h hat as h hat is equal to p square by 2 m plus v x t, and the time development is governed by the equation which you can see on this, and this equation is called Schrodinger equation. Now, you must note that this is a postulate and there is no formal derivation for this equation. Now, it can be shown that p is a differential operator and x is just a multiplicative operator. So, x psi is x times psi, p times psi is minus I h bar d dx psi. So, if we use these relations, then what we get is Schrodinger equation, which is I h bar d psi by dt is this operator which is minus h bar square by 2 m second derivative plus v operating on psi x t. This is Schrodinger equation and it defines the time development of the wave function. Now, we have a postulate regarding probabilistic interpretation of wave function. The idea is that you can define a rho x t which is psi star times psi, where psi is the complex conjugate of psi, and this is the probability density, and rho dx is probability of finding the particle at the time t between positions x and x plus dx. So, this is how we define probability density. Now, given an example, suppose we have a free particle with definite momentum, then momentum is p, energy is p square by 2 m, then this particle is going along the x direction. So, we have a wave travelling along the x direction associated with it. Then we have already seen that psi p x t is exponential I p x minus E t by h bar is a travelling wave and it describes the particle with the momentum p. Then the probability density is a star a, and the probability of finding the particle between x and x plus dx is a star a dx. What does it mean? It means that the particle is equally likely to be found everywhere and the uncertainty in x is very large. In fact, it goes to infinity. Now, this is consistent with the uncertainty principle because definite momentum implies delta p is equal to 0 and delta x goes to infinity. Wave function description is thus consistent with uncertainty principle, and it is also true in more general situation. Then we consider average or expectation values. Now, if you make a repeated measurement of various observables like position and momentum on identically prepared single particles described by wave function psi x t, then they will be spread over uncertainties delta x and delta p, and their average values can be obtained experimentally. The question is, how are they related to the wave function psi x? Now, here is some simple observations, and we see that how after all we define some averages. And here we see that if we make n observations on some variable x, then it is easy to see how we get x average. And then if this variable is now made a continuous variable, then it is very easy to see that x average is an integral of x rho x dx, where rho x dx is probability that observation yields value between x and x plus dx. This is simple probability concept. Now, what happens in quantum mechanics? In quantum mechanics, x goes to x hat and rho x dx goes over to psi star psi, then x average goes over to an integral which is psi star x psi dx. And as I have told you the properties of x operator, it is just x operator sandwiched between psi star and psi, and we are taking the integral. So, in this way we compute x average given the wave function psi. And then uncertainty in position is defined by this relation delta x square is x square average minus x average square. This is an exact mathematical statement regarding uncertainty in position, and it is a measure of how wide is the distribution of x around the average x value. Then the concept of eigenvalues and eigenfunctions. This is simply that once you have some operators, then the idea is that operator operates on the wave function and gives it a new wave function, that is O psi is phi. Now, if it so happens that phi is proportional to psi, then you have O psi is lambda psi. Then we say psi is eigenfunction of O corresponding to eigenvalue lambda, and it is a basic postulate in quantum mechanics that the result of any single measurement of a measurable dynamical variable is one of the eigenvalues lambda of the corresponding operator O hat. And similarly, we can define the momentum measurements P average. Classically, we would think that P average is P x rho x dx, but this is not correct quantum mechanically, because P is not defined for each x as it is against the uncertainty principle. So, we are led to the consideration of momentum P as a dynamical operator which operates on the wave function, and P hat is minus I h bar d dx. So, P operator is minus I h bar d dx, and then let us see what is the result for wave function for a free particle with momentum P. Now, it is very easy to see that P operates on psi p x and it gives you P psi p x, that is psi p x is eigenfunction of operator P corresponding to the eigenvalue P. Now, I talk about computing various averages, and here it is enough to note that any f operator average can be defined, can be computed about by the third line you see from the top that it is that f sandwiched between psi star and psi, and you make the integral. That is how you calculate average value of any f operator. Here I have just shown how you compute p average and p square average, and by that you can find out the delta p square, that is the momentum uncertainty. Now we talk of energy operator. Now energy operator is just I h bar d dt. Again take the example of a free particle, and for a free particle psi p is given like this, as you see here, a exponential I p x minus E t by h bar, and then E operator on psi is just gives you E times psi. That means psi p is eigenfunction of energy operator E corresponding to eigenvalue E. Now we talk about the postulates regarding measurements in quantum physics. In classical physics, an ideal measurement leaves state invariant. This is very important to note, that in classical physics the measurement does not change anything. In quantum mechanics, measurable dynamical variables are operators and they are called observables. All observables are Hermitian operators. Outcome of one single measurement is one of the eigenvalues of the operator corresponding to the observable. An ideal quantum measurement performed on a particle in any state changes this state to the state corresponding to the eigenvalues measured. This is a very important difference between classical and quantum physics. What you see here is that this wavy thing is the wave function corresponding to a particle, and when you make a measurement on a particle which is described by this wave function, then you get one of the x values. It could be x1, it could be x2, it could be x3, it could be x4. This is not fixed, it could be anywhere in this envelope. These are the different measurement outcomes of the position measurements of a particle. Now we talk of superposition principle, and this is also a hallmark of quantum mechanics, and because what we are saying is that if psi I is 1 to n are possible wave functions, then so is their linear combination. That is, psi is sigma Ci psi I summation 1 to n, where Ci are arbitrary constants. So, if psi i's are wave functions, then so is their linear combination. That is a superposition principle, and we have seen that electron two slit experiment and diffraction of electron by single slit lend support to the superposition principle. Now, it is what I want to show you, that how can we make Schrodinger equation plausible. So far we have taken it as a postulate. Now we try to see that how can we show that, well, it is fundamentally correct or it is plausible. I mean, I should say it is plausible. Now the wave functions obey superposition principle, and hence the equation governing them should be linear. That is, the power of psi and its partial derivative should be 1 everywhere in this equation. Now let us concentrate on the case of a free particle moving in the region of constant potential V, and its momentum p does not change with time as force minus dy by dx is 0. What happens to the energy? Energy is E is equal to p square by 2m plus V, it is constant, p is k h bar, E is h bar omega, and we have h bar omega is equal to h bar square k square by 2m plus V. It is the statement of the energy, how the energy is related to the frequency h bar omega and the k, that is the propagation vector, and the potential. We have seen that a free particle travelling along x direction is well described by the wave function psi is equal to a times exponential I k x minus omega t. Now we try to find a differential equation which yields right energy momentum relation, h bar omega is h bar square k square 0.2m plus v corresponding to the above wave function. Now, we have noted that it is obvious that the required differential equation should involve operator del 2 del x 2 and d dt. Now, it is easy to verify that I h bar d dt operating on this exponential is equal to minus h bar square by 2 m del 2 del x 2 plus v operating on this exponential, and this gives right energy momentum relation. So, here we have shown that at least for a free particle in constant potential V, psi p is exponential I by h bar p x minus E t is a solution of differential equation I h bar d psi by dt is minus h bar by 2 m del 2 del x 2 plus v operating on psi. Now, it has all the good features. It is linear, it allows for superposition, and the coefficient of partial derivatives in differential equations, which are I h bar and h bar square by 2 m, do not depend on parameters of motion, energy and momentum. You see, here we were trying to find out a differential equation. Generally, we have a differential equation and we try to find the solution. It is a reverse situation. I have an energy expression and I want to find out what is a corresponding differential equation, and I have shown that this Schrodinger equation is such which gives right relation between energy and momentum, and that is how I say that it is plausible. Now, the next thing is that what happens when we have the potential which is not constant, but it varies with x, and then we have a force which is minus dV by dx, and then the postulate is that the behavior is still governed by the same equation. The only thing is now V is not constant, but it depends on x. So, I get I h bar del psi by del t is minus h bar square by 2 m second derivative plus v and whole operating on psi. This is Schrodinger equation. Again, I must tell you that this is a plausible, it is not a proof from the first principle, it is just that it seems that it is correct. Now, I have the Schrodinger equations, and we have the operators E operator and Hamiltonian operator, and this slide just tells you that what happens when psi is operated by V and E operators. And what we show here is that you get the Schrodinger equation when you let E operator psi becomes H operator psi, and we get the Schrodinger equation as I told you before. Now, the question is why we accept Schrodinger equation which we cannot prove and which we have not still proved. The answer is it works, and it works well. It has tremendous explanatory and predictive power. A large number of atomic and nuclear phenomena can be explained using this equation. Second, experiments can be planned and their results predicted using this equation. So far, all such predictions have been consistent with experimental outcomes. That is why we accept Schrodinger equation even though we cannot prove it. In fact, nobody has proved Schrodinger equation from the first principle. Then we talk of time dependent and time independent Schrodinger equation. Now, the time dependent equation is I h bar del psi del t is minus h bar square by 2 m del 2 del x 2 plus v operating on psi x t. This is time dependent Schrodinger equation. Now, if the wave function psi x t can be put in the form psi is phi times exponential minus iota E t by h bar, then we get an equation which is minus h bar square by 2 m del 2 del x 2 plus v operating on phi, giving you E phi, which is the last equation that you see on the slide. And this equation is called time independent Schrodinger equation. Then what are the stationary and the non-stationary states? Now, the stationary states are those states in which the psi can be put in this form psi x t is phi times exponential of minus iota E t by h bar. And for these states, it is easy to see that the probability density rho is psi star psi is phi star phi and is independent of time. There is no time in rho. This is very important to notice, that there is no time dependence in rho. If this is the situation, then you say that it is a stationary state. Then what are the non-stationary states? Non-stationary states are those states which are of the form psi x t is sigma c I phi I exponential of minus iota E I t by h bar, where c I are constants. And for these states, it is easy to show that probability density rho is equal to psi star psi depends on time. You see, previously rho was independent of time, here it is rho is depending on time. So, when the rho depends on time, then we say that these are non-stationary states. Here I am just telling you about the various operators, position operators, momentum operators, kinetic energy operators, potential energy operators, Hamilton operators and energy operators. These are the examples of the operators which are used in quantum mechanics. Then their action on the wave function. After all, what does an operator do? As I told you, the role of the operator is it acts on psi and it gives you a new psi. So, x operating on psi is x times psi, Vx operating on psi is Vx times psi, P on psi is a differential operator. So, P is minus I h bar d dx psi, and for the psi under consideration it is just the multiplicative factor P, that is psi is a eigen function of P operator in this particular case. And similarly, the energy operator and the kinetic energy operator are eigen functions corresponding to P square by 2 m and E. Friends, what we have seen today is that in quantum mechanics, the state of the system is described by the wave function and its evolution is described by the Schrodinger equation, and we have seen that there is no proof of the Schrodinger equation. All that is that we can make it plausible. And why we accept this equation for the evolution? The reason is that it is in conformity with the experimental results. We can predict about the experiments and we can explain the outcomes of the experiments. That is why we accept Schrodinger equation as a very fundamental equation. Thank you. I hope you have enjoyed.